Namaste. Welcome to this channel Chemistry Made Easy by Dr. Ashok Mulik. Today we will see the next point of this topic, that is molecular orbitals is our present topic of discussion. Here last time we have seen the initial concept regarding the conditions or requirements for the formation of a molecular orbital. Now we will see the actual process of formation of molecular orbitals in case of these s-Orbitals. So we know that the atomic orbitals are of different types, that is s-orbital, p-orbital, d-orbitals and f-orbitals. So out of which we are considering here s type of orbitals. So here we will see how are molecular orbitals formed from s-orbitals. Now we will consider the example of hydrogen, where we find that the electron is only one in hydrogen, and there is, say if we consider hydrogen, its electronic configuration, this is atomic number Z, electronic configuration is 1s1. Here the hydrogen has only one atomic orbital like this. So this is atomic orbital, and there is only one electron like this present in the electron shell, that is energy level. So energy level contains only one electron like this. From this we will see how are the atomic orbitals are participating. First we will see the equation. Here one hydrogen, say this plus another hydrogen gives H2 molecule. This is simple form. Now we will see these hydrogen atoms and their, say this is the nucleus of this hydrogen, and nucleus of this hydrogen has this nucleus. So we will present their atomic orbitals like this. Then these atomic orbitals are having electrons like this. So the wave functions are used to represent these atomic orbitals. So first of all we know that this is one hydrogen, this is another hydrogen. This has one s orbital. So you can show this one s orbital. This is one s orbital. Now each orbital is represented using wave function psi, that is psi 1s. And for our convenience we are distinguishing them by HA. We can show this as HA and HB. So we will write here the wave function for this 1s of hydrogen, psi 1s A, and this atomic orbital or electron is represented as 1s B. 1s B. Now the process of bond formation begins. How it begins? Initially the two hydrogens are at infinite distance, but progressively they are coming together, and they are brought at such a distance so that the attractive forces and repulsive forces come into existence. So here you will find that there are two types of forces, that is attractive force and repulsive force. So when the distance is large between them, initially the forces are not existing, but when they are coming at sufficient or enough distance, the attractive forces and repulsive forces are existing. So at sufficient distance, the two forces will show that the attractive forces are more and repulsive forces are less. Again, if we try to bring the two nuclei still closer, then what we find that the attractive forces are weaker and repulsive forces are stronger. So the bond formation or formation of molecule is possible only when this condition is satisfied, where attractive forces are maximum and repulsive forces are minimum. Now you will see that the attractive forces are arising because of the electrostatic attraction between the nucleus of this atom and electrons of this atom. Similarly, nucleus of this atom and electrons of this atom will develop attractive forces. The two nuclei will come closer and they will develop repulsive forces. Similarly, the two electron clouds, when come together, they also repel each other and produce or develop repulsive forces. So, and after when these two nuclei are coming at sufficient distance called the internuclear distance or bond distance, what happens? The two electron clouds are arrayed together like mathematical terms, and this results in the formation of a large electron cloud. So, a larger electron cloud is developed like this, and this is called molecular orbital, and these two are called atomic orbitals. So, addition of these two will give us molecular orbital like this. So this molecular orbital is represented with also psi, symbol psi. Now such type of molecular orbital is obtained and it is called a sigma. Now if we see the symmetry of this molecular orbital, you will find that both the atoms also have one s orbital having sigma type of symmetry. These are this electron cloud and this electron clouds also are symmetric with respect to their bonding axis or nuclear axis, and as a result of this they are added together in the line of bonding axis, means they are overlapping with each other, or the electron clouds are merging together and giving larger electron cloud. So this formation of larger electron cloud is given by this psi sigma, and this is given by n is equal n into Ca into psi 1sa plus Cb into psi 1sb. Now this n is called normalizing factor, and it is given by integration of psi star or asterisk into this d tau is equal to 1. This is normalizing factor, and this Ca and Cb are these adjustable coefficients. When the two atoms are of same element, these coefficients are also same, and therefore their values are identical. Now here you will find that this n gives us the value of 1 upon root 2 into this psi a, psi 1sa plus psi 1sb. So here we get this equation for psi sigma, that is called a molecular orbital. So this is called this sigma type of molecular orbital. This is sigma MO, and this is also called bonding molecular orbital. Similarly, we can have the now here first of all we will see how it is formed. So here you will find that this side for 1sa and this side for 1sa have plus signs of wave function. The sign of wave function for this atomic orbital is plus. Here it is plus, not shown actually, but it is plus. And here we have also shown that it is plus. So the signs of wave functions are identical. Instead of this, we can also use the signs of wave functions for the sigma bonding like this. So instead of this, we can put here negative sign and here negative sign. Similarly, we can take here negative sign and here negative sign. So then also the sign psi sigma is same or unchanged. It means, in short, sigma type of bonding molecular orbital is formed when the signs of wave functions are identical, maybe plus plus or minus minus. It is the same. Then there is also formation of another molecular orbital. You can visualize here like this pictorially. Like this. During the formation of sigma bonding molecular orbital, they say the signs of wave functions are plus plus, or instead of this we can also show minus minus. It means it should be same. But when we have obtained this another molecular orbital called, this is sigma star molecular orbital called antibonding molecular orbital. This is antibonding molecular orbital, and this is formed when the signs of wave functions are opposite. This may have plus and then it should have minus, or this, if it has minus sign of wave function, it should have plus sign of wave function. Then such type of antibonding molecular orbital is formed. This has also the sigma type of symmetry, but the difference is that the signs of wave functions are different. Here the signs of wave functions are identical. Then electron density here, it is concentrated in between two nuclei. In this case, the electron density is not concentrated between two nuclei, but it is away from the two nuclei in opposite directions. As a result of this, you will find that the electron density is 0 along this axis, that is psi square is equal to 0. Electron density along this is 0, and therefore it is called nodal plane or nodal plane. So node is obtained between two nuclei. Now we consider the energy. This formation of sigma molecular orbital takes place with lowering the energy of this system or bond formation process. When this type of molecular orbital is formed, that is antibonding molecular orbital is formed, the repulsive forces are strong. As a result of this, energy increases. Here the repulsive forces are minimum, attractive forces are maximum. Therefore, energy of the system or this molecular orbital is lower. So these are the various differences. So addition of or presence of electrons in these molecular orbitals will stabilize the molecule, and presence of electrons in these molecular orbitals will destabilize the molecule. So these are called lobes. This molecular orbital have these two lobes. Here there is only one lobe of the molecular orbital. Now you will see that this antibonding molecular orbital psi sigma star is given by n into Ca into psi 1sa. Now if this atomic orbital has positive sign of wave function, and if we choose another sign of wave function for another atomic orbital Cb into psi of 1sb, Now we have taken that this atomic orbital has negative sign of wave function and this has taken positive sign of wave function. Or alternatively we can take this negative sign of wave function and this positive sign of wave function. Then also we will have this type of antibonding molecular orbital. Now it gives 1 upon root 2 into this psi 1sa minus psi 1sb. So here you will find that the electron density is maximum between the two nuclei, whereas here electron density is away from the two center of this nuclei. That is, you will find here presence of node where electron density is 0, and here you will find that electron density is plus, very strong electron density. Now for our convenience we say that this is z axis, so this is z axis, and if we see the symmetry you will find that this has C2 type of symmetry. This is also having same type of symmetry. Now we can show this diagram in another way. The diagram is shown in alternate. So we can take this energy axis, and now we can show the two atomic orbitals. Say this is one atomic orbital, say this is 1s. So we can represent it as 1 psi 1s a, and this is psi 1s b. So a and b are just for distinction between them. Now if we so there is only one electron here, one electron here. Now if we see the linear combination of these two atoms, when the two atomic orbitals are added together in the line of bonding axis, it is called LCAO, linear combination of atomic orbital. So after LCAO we can form these molecular orbitals. So this is bonding molecular orbital called a sigma, and it is represented as with sign of wave function, that is with wave function psi sigma, and there is antibonding molecular orbital like this. So this is sigma star, or it is also represented as psi sigma star. Now the distance between, say this is the energy axis for atomic orbitals. So being that two atoms of same element, their energies are also same. So we have represented them at same energy level on this energy axis. Now we will take this difference between these energy levels. So the energy difference between the two levels is, say, delta E1, and energy difference between these two energy levels is, say, delta E2. Then you will find that this delta E2 is much greater than delta E1. So delta E2 means this molecular orbital is much at a very large distance from this energy level for atomic orbitals, whereas this molecular orbital bonding nature is shown at lower energy level, but the distance between them is very relatively smaller. But formation of this or lowering of this molecular orbital in on energy axis shows that this gives stability to the molecule, whereas moving this of antibonding molecular orbital at higher energy level shows that this causes the destability to the bonding effect. So we have two electrons in each atomic orbital. So after formation of this sigma, you will find that these two electrons will enter into these two only one sigma bonding molecular orbital, and this will remain unoccupied. So addition of two electrons according to above principle will strengthen the bonding effect. So this is also given by bond order. So here bond order is given by 1/2 of the electrons, number of electrons present in bonding molecular orbital, that is 2, minus number of electrons present in this antibonding molecular orbitals, 0. So that will give us 1. So the bond order is 1, means their number of bonds between the two hydrogen atoms is only 1. So this is called bond order. Then you will find that there are in this way two types of molecular orbitals formed here. Now you will find that the third type of molecular orbital, that is non-bonding molecular orbital. Non-bonding molecular orbital. Such type of molecular orbital is actually obtained from the atomic orbitals which cannot participate in process of overlap or addition process. So this process shows that some of the atomic orbitals may have unmatched or different symmetry criteria, means one atomic orbital has one type of symmetry, another atomic orbital has another type of symmetry, or one atomic orbital has one type of energy, or the difference between the energies of the two atomic orbitals is very large. Then also the atomic orbitals cannot take part in bond formation, and such atomic orbitals are just transferred into the MO system and called the non-bonding molecular orbitals. So when the number of atomic orbitals participating are odd, means there is no matching symmetry orbital, then also that atomic orbital is converted into non-bonding molecular orbitals. Now you will see that the number of participating atomic orbitals are 2. The number of resulting molecular orbitals are 2. So the number of molecular orbitals, that is number of MOs, is equal to this number of AOs. So in this process of molecular formation of molecular orbitals, you will find that the number of participating atomic orbitals is equal to number of molecular orbitals formed. So in this way you will find that there are 3 types of molecular orbitals possible from this s-orbital. So with this we will stop our discussion and we will continue the topic in the next lecture. Till then, goodbye. See you next time. Please subscribe to this channel and press bell icon and like button. Thank you very much for watching this.